announcement. With regard to the school, we just posted the open problems. So check them out. At 4 today, I think, we gather again and
and don't leave before everybody is assigned to one problem.
Yes. So we need to assign you to some problems. So that will be at 4. Other announcement, we are going to test all of us again during the break. It's not fun, but okay. Please bear with us. Very important, picnics and weekend. If you want a picnic Saturday and Sunday, you need to ask now. Okay, so when you go today for lunch, there are 2 sheets of papers. Saturday, you write your name, and if you don't, you won't have picnics. Okay, and I highly recommend you don't stay in the school and you go out because the weekend is very nice. And I think we are done with the school. Anything I forgot? Okay, in which case it's my pleasure to introduce Giulio Biroli, that will be our next speaker.
Thank you.
We didn't met here, but we kind of met here at the school.
Ah, yeah, maybe.
And I hate to remind you, but that was 20 years ago.
Yes, almost 20 minutes ago.
So anyway, welcome back.
Thank you.
This time, and it's a pleasure to have.
Yeah. But we were both students. I wasn't a professor; and he was a student. I mean, just to precise. All right. So what I would like to do in my 5 series of lecture is to show you different example, methods, and idea on dynamics in high-dimensional non-convex landscape. And when I started to prepare the lecture, I realized that actually, in order to do this, I had to use, several results on random matrix theory. And then I thought that after all, actually, random matrix theory pops out in many examples in modern machine learning. It can be the correlation matrix of data. It can be the Hessian when you study training dynamics of a deep network. So actually, it was useful to not just quote all results on random matrix theory, but to give you some idea on how you can get results on random matrix theory, since if you do research in machine learning, I'm sure you will get it. And also, I think in the, Remy used some results already on random matrix theory, and there are others that will use other results. So I think it's good to give you some idea. And so today, actually, it won't be about dynamics in high-dimensional non-convex landscape, but will be a crash course on random matrix theory. And then we will start tomorrow with dynamics in high-dimensional non-convex landscape. So today, what I want to do is, as I told you, a crash course on random matrix theory, and in particular using, there are many different techniques that have been developed along the years in random matrix theory. And there is one which is particularly interesting and has been extremely, let's say, popular in the last 10 years in the math literature, which is the Dyson-Brownian motion. And so this is what we are going to study today. And this will be our technique to get results on Dyson-Brownian motion on random matrices. Also a disclaimer, as you will see, I think in a nanosecond, I'm a physicist, I'm not a mathematician, but I will try, I know that there are mathematicians, and I will try to tell you when one can do things rigorously or not. So today, all the things I'm doing can be made rigorously without any problem. Okay, and actually, then I will tell you at the end where is the frontier in mathematics on this problem. All right, so what we are going to study is what is called Gaussian, the simplest matrices, or the Gaussian orthogonal ensemble of random matrices that you saw already, I think, yesterday with Remy. So these matrices are, our matrices, they say Mij, where I goes from 1 to n. So Mij are IID random Gaussian variable, and they are defined such that Mij is, at least in my notation, will be a Gaussian variable with a variance which is sigma squared divided by n. And then actually MII, so along the diagonal, is n 0, 2 sigma squared divided by n, big N. Okay? So this is it's one of the, let's say, classic example of random matrices. It's not the first one. So these random matrices were introduced by Wigner in the 50s. He was actually interested in understanding the property of, statistical property of nuclei. So in quantum mechanics, you know, you have an operator, which is the Schrödinger operator, which is an operator in Hilbert space. When you have big nuclei, many nucleons, this operator is super complicated. And so what the hypothesis that he did is say, okay, this is a very complicated operator, very complex, so just replace this complex I mean not complex, meaning real and complex, I mean really complicated, let's say, operator. Let's replace it by something which is disorder. And this maybe is one of the first cases in which the replacement of a deterministic complex problem by a disorder problem was very successful. And he said, okay, well, depending on the symmetry of the Hamiltonian, we can use, for example, in certain cases, matrices which are of this type, which are in the Gaussian orthogonal ensemble. And actually he had a lot of success, and he explained many properties that were seen in experiments. I will not go into this, but just to tell you the story. But actually, the first example of random matrices was done by Wishart, I think 25 years before, in statistics. And I will say a few words about Wishart matrices at the end of this lecture.
These are symmetric.
These are symmetrics, yes. Thank you. Mij is equal to Mji. And I think everything is well defined now. All right, so why they're called Gaussian orthogonal ensemble? I don't know. Remy, did you say it yesterday? Why?
You mentioned they were invariant, and the measure was invariant.
Okay, so maybe I can just redo it quickly. So if you consider the probability of the matrix P of M, so let's write it. This is going to be a normalization constant. And then you have exponential of, so for each of those, you have sum over product of I less than J of exponential minus Mij square, and then you have n. So let me do it with sigma. From now on, I will put sigma equal to 1, and then at the end, I will put it back. So it's divided by 2, and then you have a product over I of exponential minus n mii square divided by 4. And then all this, I can rewrite it like same normalization constant, and then exponential. This product, I put it up, and I will write it like sum over I less than j. And I have minus n mij square divided by 2. Then actually, instead of doing I less than j, I will do I different from j, and I put a 4. Okay? And then I still have this term, so I should also sum over I equal to j, so I can just do this. Okay? And so if I write in this way, then you see that this is nothing else. I can rewrite it like exponential of minus n divided by 4, the trace of m squared. With
Explain this notation with the n.
Sorry, this is the normalization constant that I put in front. There are all the 2 pi, etc. So you see that this, indeed, this is the trace of m squared. If I consider a matrix M, and then from this matrix M, I take the matrix MO on transpose. So I do an orthogonal transformation, where the trace is invariant. So the trace of the square of this matrix is equal to the trace of M. So O transpose is equal to the identity. It's an orthogonal matrix. Okay? So this tells you that this term here is invariant if I do this transformation. So if the reference, so you know, orthogonal transformation are related to rotation. You can think in this way. I'm just rotating the frame. And this term is invariant. So this is actually, it's not enough to say that the probability law of the matrix is invariant under the orthogonal transformation. So there is another thing that I should check, which is the measure, exactly. So there is a Jacobian when I do this transformation, and I should show that the Jacobian is 1. I will not do it. You can check it. It's a simple exercise, or maybe you can even see it by general argument. So what I'm just saying is that, okay, this is invariant under orthogonal transformation. The Jacobian is invariant. So the measure, I mean, the probability is invariant, is 1. Jacobian is 1. So you have, indeed, that this probability law is invariant under orthogonal transformation, which means that if you have a matrix M, well, if you do just this transformation, these two have the same probability. Okay? So this is why it's called Gaussian orthogonal ensemble, because it's the ensemble of all matrices, and then they have this orthogonal symmetry. Okay, so what I would like to do today is to study the statistical properties of the eigenvalues and eigenvectors of this ensemble of random matrices. So I will start first with the eigenvectors, which is easy, and then I will go with the eigenvalues, which is a bit more complicated. Are there questions on this?
Is it a unique probability measure on matrices that are invariant under orthogonal transformation?
No, because actually, you see here, I could add, for example, if I mean, it's, okay, let me add it this way. I could add, for example, trace of m to the 4, and this will be also invariant. Actually, the generic way, I mean, people study, okay, let me just put this between parentheses, maybe here. So people studied measure like P of m equal to a normalization constant, again, and then exponential of minus trace of V of m, where V is a certain function. And, well, it has to be defined in such a way that this probability is normalizable. But, yes, so these are generic probabilities that are invariant under the orthogonal transformation. Other questions? OK. All right. So what I would like to do now is to understand the statistics of the eigenvectors. So the matrix are random. So the eigenvectors, which will denote V alpha, with alpha which goes from 1 to n, are also random. OK, so they are random, but they are quite simple, actually. So, well, the probability, if I look to the, what is the probability of, let's say, of V of alpha for a given alpha, well, maybe you can guess it. This is particularly simple. And because, I mean, what I'm looking at, so this V alpha, it's a vector on the unit sphere. And I know that I have invariance by rotation. So what is the probability of V of alpha? Exactly. It's uniform on the sphere, just by using symmetry. So you see, they're really, it's really simple. There is nothing complicated. So maybe something that maybe sometimes is used and can be useful to know is that, well, of course, well, you know that sum over I of Vi alpha square is equal to 1. And this means actually, well, if I take the expectation, so throughout my lecture, I will always try to use this symbol, which is the math symbol. But again, I'm a physicist. It's a long time that I don't use it. And sometimes I will put things on top, or sometimes I will put something like this. So shout at me if you see this, or just, well, OK, just a disclaimer. It could be that I will not be as good as I try to be. And, but OK, so this one, so from this, I'm going to get that for a given, in a given, so for a given, in a given direction, Vi alpha square, so this is equal to 1 over n. And actually, one can show easily, just using this property, that actually the probability of Vi alpha is roughly roughly Gaussian. So again, I will put, again, normalization constant, and here I have minus n by alpha, the alpha squared divided by 2, okay, is Gaussian. So the component of, one of the component of a given eigenvalues, you can take, so you take an axis, so let's say, let me draw it like this. So you have, let's say, this is the axis which corresponds to the direction I. And then I take one eigenvector, I take the eigenvector by V of alpha. And so V of alpha is typically orthogonal to I, almost orthogonal to I. And there is a small fluctuation in this direction. And the fluctuation is of order 1 over the square root of n. Okay? Which is, I mean, the results that I guess all of you know, that in high dimension, well, if I take one vector at random, well, if I take one one direction and I take a vector at random, this vector at random is almost orthogonal to this direction. And this is almost a Gaussian, and well, you can either do it, compute it, or it's actually, it's even, if you are a physicist, this is, you can understand it using the microcanonical and macrocanonical ensemble. But okay, it's simple. Just to tell you that the statistics of eigenvector is very simple. Eigenvectors are uniform, and if I look what one component is almost a Gaussian. Okay, questions? No? All right. So now, what about the statistic of eigenvalues? This is much more complicated and involved. So maybe before continuing, just how many of you have already seen random matrices? I'm sure. Good, almost. So how many have seen Dyson-Brennan motion? That's good. At least, okay, all right. How many have seen the resolvent technique? Okay, all right, okay. All right, so now eigenvalues. Values. Well, as I told you, there are many methods to get the probability of the eigenvalues, and what we are going to use is the Dyson-Brennan motion. And this is also a good way to see that we are all on the same page with dynamics, because I'm going to discuss dynamics, and this is a stochastic process dynamic method to get the probability of eigenvalues. I don't remember if in the file that Lenka sent about the previous knowledge, there was also, let's say, stochastic equation or Langevin equation. But so how many of you didn't see stochastic equation? Okay, perfect. All right. Okay, all right. So what is Dyson-Brennan motion? So what is the idea? So what we want to, the idea is the following. So you start with the matrix M. So M is a GOE matrix. And then you want to construct the process in time. And so you have M, let's say at time t. And now I'm going to tell you how I'm going to construct the process. So how I go from time t to time t plus delta t. So first, from M of t, what I'm going to do is I take M of t, and I'm going to add, let me check. I'm going to add another GOE matrix, which I call G of t. So this one is independent of M. And so G of t is going to be GOE. So it's GOE. But, okay, but the scaling is such that the, so let's say the Gij is going to be a Gaussian variable with variance, which is dt divided by big N. Okay? And now dt, so here you see, I mean, it's the Dyson-Brennan motion that we want to construct. So it means that we have t, which is the axis of time. And then I'm going to split this in small interval dt. And dt is going to be much less than 1. And of course, I mean, the whole problem when you want to do a rigorous proof is to show that you can take the dt going to 0 limit. And this is not something that we are going to do, but it's not, I mean, it's not particularly difficult. So for us, we'll always take dt much less than 1, and we will assume that it exists, the dt going to 0 limit. Okay, so this is the first thing. So I take the matrix, I add the GE matrix. Now, if I consider the sum of the two, well, the sum of the two is a GOE matrix, right? I mean, if I sum two Gaussian variables, I get a Gaussian variable. So, well, this is just a bunch of Gaussian variables. So, and now what I'm going to do also is that I'm going actually, so this is, I'm going to call it M twiddle of t. And then I'm going to define that M at t plus dt is by definition is going to be M twiddle divided by t divided by square root of 1 plus dt. So why I do this? Because now, if I look at the matrix M at time t plus dt, so M at t plus dt is GOE also. And if I consider an element, so of M, so Mij t plus dt, so let's say, and I take the expectation, then this is going to be, so in on the, here when I take the expectation of m twiddle square, I'm going to get 1 over n plus dt over n from the numerator, from here. And then below I get 1 plus dt. And so this gives me 1 over n. Okay? So this means that this matrix mt plus dt is a GOE matrix with exactly the same variance of m of t. So I'm just constructing, and let's say, so I go from, let's say, this ensemble to this, from this statistically to this matrix to this one, but these are both belong to the GOE, both with the same variance. Okay? Yes.
So just noting one question. So this arrow where you write MT, right arrow, MT plus GT, what does it mean mathematically?
I'm just saying that, I was just saying that I take M, I add G, this is my matrix M twiddle. So let's do it this way then. Okay?
You define M tilde by M, and then you define MT plus DT by M tilde.
Yes. Okay. And so now the idea is that, imagine that I have, so the probability, so this is a stochastic process. And in this stochastic process, so you can think that I have time t. So remember here in principle, I discretize, but I will take the continuum limit. And then I have at time t, so let's say that this is the time here, this time here. I have all the eigenvalues. So the eigenvalues, I will denote them like with this point. So there will be lambda 1, lambda 2, etc., until lambda big N. And now when I go from t to t plus dt, this eigenvalue will change. So I don't know, will be here, for example. Okay. And now let me take the continuum limit. So I will have in the continuum limit, I have this curve of eigenvalues that move. So they are just like particles that are undergoing a stochastic process. And what I'm interested in is the probability p of lambda 1, lambda 2, lambda n. So in principle, this stochastic process, this probability should depend on time. But exactly as I told you, so what is here, the matrix M and the matrix MT plus DT, they have the same variance. So what I'm interested in is really the invariant distribution. So P lambda 1, lambda 2, lambda n, which is interesting for us, will be the invariant distribution or the stationary distribution for this stochastic process. And now this stochastic process is, we will see, it's really like particle in one dimension that moves, interact, and they are subjected to some kind of noise. Yes?
Should we not worry about crossing eigenvalues?
About?
About crossing?
No, because actually when dt goes to 0, you can show that they never cross. So they always remain like this. And we will, well, I will try to give you an argument, but yes, they never cross. Other questions? Okay. All right, so now let's try to see what is this stochastic process, which is what is called the Dyson-Bernal motion. Okay, so, well, let's do it. So m at time t plus delta t is equal to, well, I just used the definition that I gave before, is equal to m of t plus g of t divided square root of 1 plus dt. Now, it's important to understand what are the different order of this term. So m of t is something which is order 1, okay? It means order 1 with respect to dt. So this one, it's of order what? Well, you see g is a GOE with a variance dt over n. So in terms of dt, I will not care about n for the moment. For the moment, n is finite. I'm not taking the n going to infinity limit. So g is of order square root of dt. Okay. So now I'm going to, when dt is small, I'm going to replace this by m of t plus g of t. And then, while the denominator is going to be 1 plus 1/2 dt, which plus, okay, which I'm going to write like m of t plus g of t 1 minus 1/2 of dt plus terms which are of order dt? No, there is a, okay, let me see if I'm forgetting something. So it's dt square or it's dt to the 3/2? It's, yeah, it's dt square, which goes up. Yes, you're right. It's dt square. I think so. In my notes, it was dt to the 3/2, but it's dt square. I think I agree. OK. All right, so while we have this term, so here it means that we have, you see, here we have a term which is of order, so this, OK, let me write everything. So we have m of t, which is the term of order 1. Then we have minus 1/2 dt m of t. This is a term which is of order dt. Then we have minus gt divided by 2 dt. And then indeed we have order of dt squared. All right, so now, well, the interesting thing is that
There's a GT missing, right?
I'm lost at dt.
A GT, G of T.
The GT is for the dt to the power 3 by 2, so you should keep the other one.
So you write GT dt divided by 2.
Sorry. Thank you. Yes. Right. OK, this is what I wanted indeed. This was y up plus order dt to the 3/2. OK.
It's plus g.
Thank you.
Without 2.
Without 2. Great. All right, so now what you have here is that this term here is, so it's much smaller than this one. So when dt goes to 0, so it's of order dt, this is of order square root of dt, so I can use perturbation theory. So if I know actually all the eigenvalues here, at all the lambda alpha at time t, what I want to know is all the lambda alpha at time t plus dt, and I can use perturbation theory because this is small. So now I will write the equation for imperturbation theory. Lambda alpha t plus dt is going to be equal to lambda alpha time t. And then let's call this matrix, so I will use the same notation. I will call it dm, like a perturbation. And now we'll use, OK, just the notation, the physicist notation for, I mean, it's physicists learn perturbation theory when they do quantum mechanics. So I will use the notation from quantum mechanics, but it will be self-evident for you also if you didn't do it. So there is one term which is the first order term, which is this one. So it's the alpha element of delta m. And then you have plus sum over beta, different from alpha, of, well, d delta m alpha beta square lambda alpha minus lambda beta at time t. And this at time t. OK, plus corrections. OK? Sorry? And yes, so the alpha, indeed, the alpha are the eigenvectors associated to the eigenvalues lambda alpha. So this is the component alpha. So in the basis that diagonalize the matrix M at time t, this is the component M alpha, and this will be the component alpha beta. Exactly, yes. So yeah, we call, so the alpha are the eigenvalues, are the eigenvectors, and we call it before V alpha. And I will just forget this notation very soon so that it's not confusing for anybody. All right, so let me write what this is. So this is going to be lambda alpha of t. Now plus alpha delta m alpha. So, OK, again, stay with me so that if I forget minus and plus sign and 2, minus 1 over 2. So this is going to be dt. So the alpha of m is just lambda alpha of t. Hope you agree. And then there is this term, which is going to be plus G alpha alpha. Okay, so here I take the alpha alpha component of M. Alpha is an eigenvector of M, so the alpha alpha component is just lambda alpha. And then I take the alpha alpha component of G. Okay. And then plus, here I do sum over beta, which is different from alpha. And then here delta M is contain M and G. But actually, I mean, we are exact to the order dt to the 3 alpha. So, okay, let me see. So there is a first term, which is G alpha beta square divided by lambda alpha, lambda alpha t minus lambda beta t. Okay, and this term here, this G alpha beta square, it's of order dt, so I should keep it. But then, I mean, the cross product or this term square, they go inside this. So this is just order dt to the 3 half. Okay. All right. Okay. So, well, now we lose also another property. So the matrix G again is a Gaussian orthogonal matrix. So it means that also in the basis, which diagonalize M is a Gaussian orthogonal matrix. So it means that, I mean, G alpha alpha is a Gaussian variable with the with the variance that we know, since it's GOE, and this is a Gaussian variable, and they are uncorrelated. Okay. You ask me a question if I'm going too fast. I had to understand exactly what you know, don't know, and so. All right, so this is the equation. So let me write it on the other side and simplify. We are almost there. Okay, so I will bring this on the other side, and then I get d lambda alpha dt. So let me also divide by dt. So I will have d lambda alpha dt, which is equal to minus lambda alpha t divided by 2. So this is this term here. Then there is plus g alpha alpha divided by dt. Okay. Plus, okay, now there is this, this other term. So this other term, I'm going to write it in the following way. So I first consider what is its average. So this term is stochastic for many reasons, because the lambda are stochastics and the g are stochastic. But for the moment, let's consider that the lambda time t are fixed. And now the g are new stochastic variable that arrive when I go from t to t plus dt. Okay? So if I compute the expectation with respect to g, so of this, I'm going to get, so this average is going to be, so I erase it, but it's dt, so the expectation of all this is going to be equal to dt divided by n, sum over beta, different from alpha, of 1 over lambda alpha t minus lambda beta t. Okay, do you agree?
I have a question.
Yeah.
How did this term pop up?
Which one?
First, this cross term, G alpha beta squared divided by lambda alpha.
This one?
Yeah, that one. Yeah.
Well, this comes when you do when you compute how the eigenvalues change. So if you have a matrix M and you add a small matrix, so you compute in perturbation theory in this matrix, which is small. Let's say that you put an epsilon in front. You compute how the eigenvalues change, and this is the equation. So I didn't prove this equation, but you can you can do it easily. Maybe later, or I can show you. So this is just come from, let's say, a few lines of computation when you do perturbation theory and eigenvalues. Okay. Well, I'm sorry. But we can look at it later. Or I mean, if you Google perturbation theory in quantum mechanics, which I mean it doesn't have to be in quantum mechanics, but it's just linear algebra. But you will find very easily on Wikipedia this explanation of this equation. Okay, so the average of this with respect to G is this term. So let me write. So now the average of this. So I will split this one in plus 1 over n. Sum over beta, different from alpha. So the dt is not there because I put it there. 1 over lambda alpha t minus lambda beta t. And then in principle, I have plus, so let's say the fluctuations. And the fluctuations, I mean the fluctuation of this term, okay? Because I took this term here, and I replace it by its average, and then, well, there are the fluctuations, okay? Now let's look at the different, and then always there is a plus, well, dot, 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 that are not important when dt goes to 0. Okay, so now let's look at the different order that we have. So this term here, it's of order 1. Or maybe let me just for the moment put back the dt here. No? Yeah, no, okay, let me put it here. Okay, no. All right, so this is of order 1. This is of order 1 over square root of dt. Remember, the g alpha alpha is of order square root of dt divided by dt, so it's of order 1 on square root of dt. So this is why I didn't want to, okay, well, anyway. So this one is of order 1. And then you have fluctuations. And now the fluctuations are of order, so if you compute them, so there is a g square, which is of order dt. So the fluctuations are of order 1. I mean, if you do it, so there will be fluctuations of order 1 here. So you have just to, you compute it from this, but you see that g squared is of order dt, so its fluctuation will be of order dt. So it's a variable with a mean of order dt and fluctuation of order dt. So when you divide by dt, it becomes of order 1. Yes?
So basically, you approximate this sum on the third term by its expectation.
Yes.
And why is it concentrating around its expectation?
Exactly. So this is the point I want to make now. So now I have a stochastic equation. I'm taking, yeah.
Are we going that it will concentrate? Because then the fluctuations should be smaller than the mean.
Exactly.
The fluctuations should be smaller than the mean. Yeah, this is why I wanted to have the dt, which was, that's the problem. Okay, let me put back just for the moment the dt, and then it's going to be a bit clear. I think it's, maybe I'm, okay, I have a dt here. I have no dt. I have a dt here. And then I have fluctuations which are of order actually dt. Now, all right, and this one, so this one then is of order dt. It's of order square root of dt. And this is of order dt. And this is of order dt. Now the thing is that what I'm not doing is that I'm not doing the limit delta t goes to 0. But when you have a stochastic equation, actually, there are two terms that are, let's say, that fight one against the other. There is the deterministic term, which is of order dt, and then there is a stochastic term, which is of order square root of dt. So this fluctuates, this not. When you take the dt going to 0 limit, and you show that there is a limit, this is the scaling that the term has to have to be. So the stochastic one has to have a square root of dt, and the deterministic one should be of order dt, okay? So if you have fluctuations, stochastic fluctuations, which are of order dt, you just don't care. They disappear when dt goes to 0 because they are much smaller than this term. Okay, so this is why I can just throw them away. And of course, I'm not proving this. I mean, this comes if you do the proof of the dt going to 0 limit. But you can also try to work out, I mean, just with small step, you try to put this fluctuation of order dt, and you will see that in any case, they are much smaller than this one, and they are less important. There was a question? No. Okay, so this is why I forgot them. If you do carefully the dt goes to 0 limit, then they are going to disappear. So I go back to the ill-defined physics way of writing this equation. Dt No dt. Okay, all right. So now, this is one here. Okay, so let me write this equation in two ways. One is the physics way, and the other will be the math way. Okay, so if I write it in the physics way, this equation I'm going to write it in the continuum limit in this way. So it's d lambda dt equal to minus lambda alpha t divided by 2 plus sum over beta different from alpha of 1 over lambda alpha of t minus lambda beta of t. And then I will put plus a noise, so a white noise, eta alpha of t. And the white noise, expectation, is eta alpha of t, eta beta of t prime is equal to 2. Let me check the 2. Yes, I think there is a 2. Not sure about the 2. Okay, well, maybe, okay, there is delta alpha beta, delta t minus t prime. So this is the Dirac delta, and this is the Kronecker delta. And so how do we get this? Well, the fact is that what is eta alpha here is nothing else than...
There is the 2, because you define the diagonal elements with the...
Great. Thank you. Yes, so now we'll show you, yeah, I was missing. So how do I get? So the eta alpha is nothing else than g alpha alpha divided by dt. And now, so now if I look at what I have here, what this means is that this is g alpha alpha divided by dt, g beta beta. So this, let's say, at time t. This could be time t prime, is the one that I sum at time t prime, dt. Now, these two are independent if alpha, well, E different from beta and T different from T prime. So from this, I'm going to get delta alpha beta. Then I get delta TT prime. And so if alpha is equal to beta and T is equal to T prime, then I get 1 over dt square. And then the expectation of G square was 2 dt divided by n, which means I get delta alpha beta 2 divided by n, delta tt prime divided by dt. And this is nothing else than the, let's say, the discrete version of the Dirac delta in the continuum limit. Okay, so this is how you get it.
Just drop 1 over n in front of this one.
Yes, thank you. There is a 1 over n. So let me check indeed. Yep. So this is, well, this is a Langevin equation, what in physics we call the Langevin equation, for any interacting particle. So here I didn't take n large. So this is defined for any n. It can be 1, 2, 3, or n which go to infinity. So in the so physicists write this equation in this way. It's not, I mean, it's not well defined if you write in this way, because the derivative of lambda alpha with respect to dt is not defined, because this is like a Brownian motion. So actually, if you want to define in a way which is, let's say, reasonable mathematically, you would write it like d lambda alpha of t equal to minus lambda alpha of t divided by 2 dt plus 1 over n. You just put the dt up. And here you would have plus a, so see, let's see the notation. So it's Brownian motion, and then with the square root of 2 divided by n in front. Okay. So in this way, everything is well defined. And indeed, I mean, you can, as I told you, this can be proved rigorously. Yep.
dt on the second term?
Sorry?
dt on the second term?
Yes, thank you. All right. So, well, now we have the stochastic process, and now what we can do about with this equation. So, what we were going to use, so this is an interacting particle. So it's a Langevin equation, so particle coupled to a heat bath. And what we are going to see is that this, we can interpret this like a gradient of an energy. So what I mean is that I can define an energy such that dV d lambda alpha is equal to minus lambda alpha divided by 2 plus 1 over n sum over beta different from alpha of 1 over lambda alpha minus lambda beta. So there is a V such that this is true. And what is this V? Well, it's simple. V is equal to sum over alpha of lambda alpha squared divided by 4 minus 1 over n sum over alpha less than beta of log of lambda alpha minus lambda beta, absolute value. And so now the equation has a pretty nice form. So the form is the following. So it's minus dV d lambda alpha plus eta alpha of t. So these are really, yes, sorry.
When you find it's alpha smaller than beta, you change no, it's alpha different from beta.
Let me check. So when I take the derivative, no, I think it's fine because when I take the derivative with respect, so if alpha is less than beta, when I take the derivative with respect to alpha, I don't get any factor of 2, which I don't have here. So if what I mean, when I derive with respect to alpha, I should take all the terms in which there is one alpha and all the beta.
I'm sorry, what is D capital B alpha?
Sorry?
What is, in the second line, what is D capital B alpha?
This is the Brownian motion. I was writing in a way that is more, I mean, would be natural for a probabilist and a mathematician. So it's the increment in a Brownian motion from t to t plus dt. Yes?
The second term in the potential is what stops the eigenvalues from causing.
Yes, exactly. So let's look at the physics of this, or of this potential. So what is this potential? So for each particle, what you have, so for each lambda alpha, now I think to the lambda alpha really like a particle in one dimension that move. And what is the potential that we get? So we have that each particle will feel a quadratic potential here, so which means that its particle is trapped. It's trapped in a quadratic potential. This is the lambda alpha squared divided by 4. I'm looking, I mean, and then you have interaction between the particle, which are log interactions. So the particle don't want to be close because if you see if they are very close, the log will blows up and it blows up to minus infinity. So you get plus infinity. You go to very high energy. So there is a log repulsion. So there is quadratic trapping potential plus log repulsion. And indeed, because of this log repulsion, in the continuum limit, they never cross. Okay, so, yeah.
We're going to be confused about it. How do we consider that? Because if I look at long time, they will cross. I mean, they will...
Never. I mean, if you do dt going to 0...
No, dt go to 0, they're
first.
not first.
Huh? Not first.
But, I mean, if you look at them over a long time, then they will always...
Yes. If you do... I mean, if you say the final time is tf, but you do dt going to 0 limit first, they will never cross. Okay, maybe we can discuss later. Why?
Instead of crossing the exchange, in a sense.
I mean, it's when they are discrete, yes. When they are discrete, you cannot really say if one is the continuation of the other. But in the dt going to 0 limit, they don't cross. So you should take 2 and look when they are really, really close, but the trajectory will not cross. Will do like this. Because you have, you have 2 Brownian, they are colliding, but then there is this log repulsion, and the way you do like this. Okay. Well, maybe we can discuss this more.
But from far away, it looks like if they were.
Yeah. If you look from far away, when they are very close, I mean, they look like they have crossed, but really they don't.
So I understand what is Brownian motion. I don't really understand what is eta in terms of my analysis.
What is?
Eta alpha.
Well, it is the derivative of the Brownian motion, which does not exist. So this is why. So I mean, it's so you see, I mean it. This is why I wrote it this way. Yes, indeed. But okay, I mean it's. I mean, this is how mathematicians write. So this is the good way if you, I mean, mathematicians want to have everything well defined. In physics books, you see this. But I mean, physicists know that in the reality, I mean, this doesn't exist when dt goes to 0. But they like it because without noise, it's something that we are used to. And then we put the noise, but then we are careful. I mean, it's we do Ito computation, I mean, Ito calculus, etc. But yeah, this is the physics notation that you will find in books.
Sorry,
Yeah.
to get back to this, but so just to understand the crossing, how did eigenvectors? So the eigenvectors are continuous.
Yes.
But then, how did when the eigenvalues almost cross?
Yes.
How did
They really they change very fast. So when I will say something later, maybe at the end. So one can write a similar equation, Dyson-Brownian motion for the eigenvectors. And so when the eigenvalues are very, very close, they will start to move actually very fast, the eigenvectors. And actually the scrambling of the eigenvectors, which is something that has been studied a lot, is really due to the eigenvalues coming very, very close. Okay, so I think it's what I like of this way of getting results on eigenvalues is that you have this interpretation in terms of particles that move in this trapping potential with log repulsion. And, well, if you are used to dynamics of interacting particles, it can give you a lot of intuition of what's going to happen. So the first thing that we can get now is the probability. What is the probability of P? Maybe, where can I write it? Here. What is the probability of the eigenvalues? So what we are looking for is the stationary probability or the invariant probability distribution under this stochastic process. So well, this I can erase. And this I will leave it. So P of lambda 1, lambda n is the invariant probability distribution under this stochastic process. So, well, what is this invariant probability distribution? From physics. So you have a system is coupled to a heat bath with a certain temperature, while the invariant probability distribution will be just, okay, normalization, and then it's the Boltzmann law. Is exponential minus V divided by T, which is the temperature. Now the temperature here, so eta alpha of T, eta alpha of T prime. So if this was a Langevin equation, this will be, I should write it like twice the temperature delta T minus T prime delta alpha beta. So which means that for us, the temperature is equal to 1 over n. Which is also telling you that we are in a regime, when n is large, we are going to be in a regime of very small temperature. Okay? So now I'm making a jump again, if you, I mean, if, but everyone raised the hand when you say that if you saw stochastic process. So it's, you know that, I mean, it's, if you have an stochastic equation like this, the invariant probability measure is this one. I mean, there are different ways to prove it. One is to write the Fokker-Planck equation for P. I will not do it. This is, let's say, a standard result. And from physics, well, you know that the invariant distribution will be the Boltzmann law. It's equilibrium. The system goes to equilibrium. Questions? Yes.
Is this technique also called this Coulomb gas technique?
Yes. Yes, this is called the, so this is, let's say, this is called the Coulomb gas potential. And this is why, actually, it's not the technique really. I mean, it's, let's say, The technique that I show is the Dyson-Brownian motion. But it's true that once you have this V with this interaction, this is the Coulomb gas potential. And so the probability law that you get is going to be, this probability law will be the probability law of the Coulomb gas potential, so it will be a Coulomb gas technique. Yes?
Where's the Coulomb gas in 2D, right?
Is the,
Interaction is
yeah.
basic,
Yeah,
but it's confined.
it's confined. Yeah. Questions? Yeah.
So what is big T in this our out also?
What is T?
Yes, the big T. Do we have
Big T, sorry. So big T is the temperature in this. So what I meant is that when you have an equation like this is called a Langevin equation. And in physics, the variance of eta, so eta of T is, sorry, there was a beta here. It's a white noise. And here is the temperature of the system. So this is a system coupled to a heat bath with temperature T. And so just I make the translation. So in our case, T is equal to 1 over n, because I got 2 divided by n before. So this, what I meant is this is like interacting particle, which interact with that potential, and they have a temperature which is 1 over n.
So, but this T must appear somehow in the mathematical writing, right? With the
No,
Brownian motion.
I just redefined. So what I got before was 2 divided by n.
Yes.
And then I'm just saying, OK, if I define T like 1 over n, so I replace this by T. And then, well, but I know that, in physics, this would be the temperature. OK, so let's write what is this. So this will be the normalization factor. And then I have exponential of, so let me write it. So it's minus T, 1 over T is n, so it's minus n. And then I have sum over alpha, lambda alpha squared divided by 4, minus 1 over n, sum over alpha less than beta, log lambda alpha minus lambda beta. That I can rewrite like exponential of minus n, sum over alpha, lambda alpha squared divided by 4. And then this, you see, if I take this minus 1 over n, minus n, they go away. So I get just the sum over alpha less than beta. So this I can rewrite like the product of alpha less than beta of lambda alpha minus lambda beta, which is an expression that you see in general for the probability law of the eigenvalues. OK, so now we have the probability law of the eigenvalues. You can, depending how you like it, it's as this form or this form. It's the same. OK? For any n. There is no large n limit. In general, many of the techniques that are used in random matrices exploit the large n limit. Here is n is finite. It's exact for any n. All right. Questions? Yes.
What I don't understand is that we arrived to this equation choosing carefully the perturbation in the beginning. If you would have chosen a different perturbation, you would have got the same distribution or not?
You mean perturbation, you mean the way in which I
little g.
The?
The little
Well, but yes, I construct little g in such a way that I know that this one will be the invariant probability distribution of the stochastic process. So I choose it in this way. So this was my guide. So I wanted to have a stochastic process that has an invariant probability distribution that is the one that I want to compute. So this was my guide. So of course, if you define it a different way, then this will not be the invariant probability distribution. So everything is going to be different. Yes, there was a question here, a question there. Yeah.
I understand what is two-dimensional. Before I heard the question, this is a two-dimensional Coulomb gas. Where I should look for the two-dimensional?
No, there is no two-dimensional. Everything is in one dimension. No, don't worry. Yeah, it's just the form. It's about the form of the potential. Why we call it a Coulomb gas, but that's not a problem. Just think it's one dimension, and it's called a Coulomb gas.
Can you
Yes.
sketch the probability distribution for different temperatures?
Well, it's complicated because I have n particles, so I don't know how to do it. But what we are going to do now, we are going to study, so you studied with Remy yesterday, the distribution of eigenvalues. So now the distribution of eigenvalues is nothing else than the density of this n interacting particle system. So this is what we are going to study now. All right. Okay. What should I erase? I erase here. Okay, so now what I want to study is the behavior of rho of lambda, which is the density of eigenvalues that you saw yesterday. You know already the result is the semicircle. You saw it yesterday with Remy. So rho of lambda d lambda, you can write it like sum over alpha of delta lambda minus lambda alpha d lambda. Okay, so this is going to be, so it's, we know already what it should be, roughly speaking. So again, let me write again what is each particle. If you think each particle what it does, so it feels a trapping potential, and then it has a log repulsion with all the other. So there are two competing terms. The potential would like to put all the particles here, all the eigenvalues here, but you cannot do it because they all repel. So well, they're going to push one with the other. So what you are going to get is that the density here is going to be something like this. We don't know exactly what it's going to be yet. I mean, you know because Remy told you, so it's going to be the semicircle. But you can expect that it's going to be something like this because, well, it's trapped, and then each eigenvalue fits a repulsion with all the others. So they cannot go all here. They will go around here. Okay, so this is what we want to compute, and we want to study what is the behavior of rho of lambda when n go to infinity. What is the statistics of the density of eigenvalues when n go to infinity. So now what I'm going to do, I want to compute the probability of rho of lambda. So this is a field or a function. I want to compute what is the probability of rho of lambda. This is going to depend on n, and I want to understand how this depends on n, big N. Okay? So in order to do this, I'm going to use, so you see here, if you look at this expression, let me erase this.
Here, rho is the sum of the rows, right?
Yes. So I'm going to be.
You need some weight to make it.
So I'm not going again. I'm not going to do it carefully, also because there is not much time. So what I'm really interested in is the probability of, let's say, of rho of lambda, where rho of lambda is going to be the histogram. So in principle, I should fix a small interval delta. So let's say that I divide this in a small interval delta, and then I want to know what is the probability of, let's say, this histogram when n go to infinity first and delta going to infinity later. Sorry, n go to infinity first and delta goes to 0 later. So in principle, I shouldn't write with Dirac delta. But I'm going to do it just to show you what is the hunch behind the results, and then you can do it carefully later. Okay.
Yes, I understand, but I was just saying that in this form, this is not a probability density, even with the Dirac.
This one? No, this will be the empirical distribution of the eigenvalues.
1 over n.
Ah, sorry. Yeah, but you're right. I should put the big N here. Okay, thank you. All right, so if I do this, indeed, terms like sum over alpha, lambda alpha square, they become, if I use this definition, they become big N, integral over d lambda, rho of lambda, lambda square. I just use the definition there. So this is rho of lambda is like the histogram. So well, sum over alpha, lambda alpha square, it's n times the integral over d lambda, rho of lambda, lambda square. So I can rewrite, actually, let me rewrite the probability P of lambda 1, lambda n, lambda 1, lambda n is going to be equal to exponential of, so there is a first term which is going to be minus n square integral over d lambda, lambda square, rho lambda divided by 4, which correspond to this one. And then there is this other term, which has 1 minus n, which is going to give me plus, there should be 1/2, I think, that I don't have. Yeah, I think there should be 1/2 here. 1/2 the n square, the integral over d lambda prime of rho of lambda prime, and then log of lambda minus lambda prime. Now, there is actually one term more, because when I do, what I did here is that I just write this like 2, and then sum over alpha different from beta, and then this sum I rewrite it with the 2 integral. So there is one term which is correspond to alpha equal to beta, in which in principle I would have log of 0, which is not well defined. So what I'm going to say is I regularize the log. So let's put a twiddle on the log. And I regularize in such a way that, let's say, log of x, log twiddle of x is just equal to log of x plus epsilon. Okay? And I keep epsilon small. I take n going to infinity first, and then epsilon going to 0 later. And so if I do this, then I will just have a term which is minus n log of epsilon, which is added to the formula. Okay? All right, so but now the important thing here is you don't care about this term, because if you are interested when n is large, you see that you have an n square here and n square here. Okay? That's the important thing. So you see that the probability of the eigenvalues, you can rewrite it like something which depends only on the density of the eigenvalues. And you have this function, which depends on the density of the eigenvalue, is multiplied by n squared. Now, what we want is the probability of rho of lambda. So the probability of rho of lambda is going to be equal, well, to this. You should, in principle, marginalize this probability distribution over, all the distribution of lambda such that they have the same rho of lambda. Okay? Is it okay for you? No. So here I have a probability of lambda 1, lambda n. So in principle, I should write here, I should integrate over let's say, I write it formally, d lambda 1, d lambda n, delta of, let me write it this way, rho n of lambda minus rho of lambda, p lambda 1, lambda n. Okay, I'm just marginalizing. Okay, I integrate over all the distribution of all lambda such that the rho of lambda, which corresponds to this eigenvalue, is equal to rho n of lambda. Okay?
This probability of rho n lambda is taken over the lambda alphas. Because rho n lambda is the formula on the left top, right? The top left formula for rho n.
Yeah? Yeah, this one is this one. Yeah. So this is a stochastic variable because it depends on the lambda alpha. So I integrate over all the lambda alpha such a way that the corresponding rho is equal to, well, the function that I put. So you should do, so what we found is that this thing here just depends on the rho of lambda. So let's rewrite this. This is going to be exponential of minus n squared, a certain functional of rho of lambda, that I will rewrite. So this function of rho of lambda, which contains this term and this term. Then there is minus n log of epsilon. And then in principle, I should compute this term here. Okay? I can do this because, sorry, I should write it. Okay, and then I have the integral over d lambda 1, d lambda n of, I didn't want to go through this, but well, rho n lambda minus rho of lambda. I think it's correct. Yeah. Okay, so this is just an entropic factor. So it means I have n particle. What are all the possible ways in which I can distribute the n particle in such a way that their density is equal to what I want? And this is a computation that it's very easy. You can do it later. It's, I guess, physicists, they saw it several times. So this is entropic. So this is like the energy term. And this is like the entropy term. Now, this entropy term is not, I'm not going to do the computation because it's not, we don't care about it. You will see it now. So it's not important. So let me recap what we got. So this entropy term, let me write it here, the entropy term, if you do the computation, and well, it's an exercise, I suggest you do it, it's going to be equal to minus n integral over d lambda rho of lambda log of rho of lambda. So I mean, it's not a surprise. This has a kind of form of like a Shannon entropy. And you can compute it easily. But the important thing is that in front, you have a factor of n here. Whereas here, you have a factor of n squared. So when n is large, the only term that counts is this one. So what we found is that the probability of rho of lambda satisfy a large deviation principle with what is called, well, I think in math is called rate, f rho of lambda, or no, maybe rate is n squared. I mean with, okay, large deviation principle, let me write it this way, which is equal to exponential minus n squared f rho of lambda. So I just forget all the other term because this is the one which is important. And f is equal to minus integral over d lambda, lambda squared divided by 4, rho of lambda, plus 1/2 integral over d lambda prime, rho of lambda prime. Yes, okay. Okay, so now in principle you know what is the probability distribution at large n of rho of lambda. Sorry.
It is a log of lambda.
Aha, sorry, thank you. Okay. Questions? Okay, so now that we know this, we know many things actually about the statistics of rho of lambda, which I want now to discuss. Can I raise here? Okay, again on the Excel file, there was one question: is everybody is fine with saddle point and Laplace method? I think it was okay, but I mean, let me just tell you. So if I had just one variable, and I have the probability of one variable x, which is equal to a normalization constant and then exponential of minus n squared, and then a certain function of x, then I know that the statistic of x and will be given by x will be equal to x star, where x star is the minimum, is the global minimum of f. And then you will have fluctuations here, and the fluctuations will be of order 1 over n around x star. So here it's exactly the same thing, except that instead of one variable, you have a function. So what it means that rho of lambda will be equal to, let's say, rho star of lambda plus fluctuations which are of order 1 over n. So when n is large, rho will concentrate around its mean, plus fluctuation which are of order 1 over n. And now how I can compute rho star of lambda? So what you can do to compute rho star of lambda, and we are not going to do it, is to you have to take, well, the minimum of f plus the constraint that the integral of d lambda rho of lambda is equal to 1. You can do it. You just run the Lagrange multiplier. You take the derivative. You get an equation. You can solve it. It's called, in math, it's called a Tricomi equation. And actually, if you want to see how you can do it, you can see a paper by Nadal, Majumdar. I mean, this is just, they do a complicated case, but you can see the technique here is 2010. But again, it's not, I mean, people knew how to solve this equation much before. It's just that here you find something which is very explicit. So you can do it, or otherwise, you can verify that the solution that I'm going to give you is the solution of this equation. And this is just the semicircle law, which is 4. I put back the sigma, which I put to 1 at the very beginning, 4 sigma squared minus lambda squared, divided by 2 pi sigma squared, which is the Wigner semicircle law. Which is just this form between minus 2 sigma and 2 sigma. And remember, I mean, this is what we find. So you remember at the beginning, I told you we have n particle. There is this trapping potential. So they all would like to be in 0. But then there is the log repulsion. So they cannot be all in 0. And at the end, this is what you get when n goes to infinity. Now, when n is not infinity, so if n is large, what you're going to get fluctuations. So you will have the true one will be, let's say, something like this. And now the fluctuation here are of order, what? Which is the order of the fluctuation? I mean, it's simple. 1 over n squared, 1 over n, indeed. It comes from the large deviation principle. And then the eigenvalues here, well, they have it, well, you know that you have n eigenvalues. They are all between here and here. So the typical gap here is of order 1 over n. But then close to here, actually, the gap becomes larger. And it's 1 over n to the power 2/3. And this, I think, was discussed yesterday by Remy. So,
can we get a distribution of the gaps?
Yes, we can get the distribution of the gaps. This is, yeah, I will say something at the end later. This is, I mean, this, I would say these are the simple things. The distribution of the gaps are the difficult things, but yes. And I will say something on the distribution of the gap later. Okay, so now the important thing here is that this large deviation principle tells you that imagine that what is the probability of, if I draw a random Gaussian orthogonal matrix, that I don't see the Wigner semicircle, and I see something in which there is a fraction of eigenvalues. So I have, let's say that this is a probability of seeing, I don't know, instead of seeing the semicircle, I'm to see something like this. Okay? A function which is really different, meaning that I have transport a finite fraction of eigenvalues somewhere else. So if I move a finite fraction of eigenvalues, I'm going to change rho of lambda. If I change rho of lambda, I'm not at the minimum of f. So the probability is going to, this is going to cost me n squared, exponential minus n squared. So the cost to have fluctuations in rho of lambda, so fluctuation that really change the distribution, so in which you have a number, a finite fraction of eigenvalue that moves. It's of order, so this probability cost, it's of order exponential minus n squared. And so this is important for, I mean, some computation that I'm going to do on Monday. Okay? Now, if you want to, instead of see a fluctuation in which, let's say that you find this, but you have one eigenvalues that it's not, I mean, here all the eigenvalues are around the semicircle, and they are between minus 2 sigma or 2 sigma, and then you have a small fluctuation here. So imagine that I want to see what is the probability to find one eigenvalue which instead is here. So what do you think? What is this probability? We know the probability of the eigenvalues, lambda 1, lambda n, if you have it in your notes. So from this, how much is going to cost to pull out from the semicircle one eigenvalue? Exponential minus? Exactly. Why? Huh?
Because Remy told us yesterday.
Yeah, it's minus n because, well, you see that the, I mean, if you look at the expression of the eigenvalues that we consider, for each eigenvalues, there is I mean, the contribution of each eigenvalues in the probability is indeed exponential minus n. Then there is lambda alpha squared divided by 4, and then there's the interaction, which is a kind of mean field interaction with all the other. So if I take one and I really pull it out, yes, I'm going to pay something which is of exponential order of exponential minus n. And also this maybe we are going to discuss. So because to have fluctuations in one eigenvalue, so let's say that pops out of the semicircle, it's of order exponential minus n. Okay, so I think it's what I don't have the time to do. I wanted to do phase transition and having a signal associated, added to the random matrix, but instead I will just conclude, well, in 10 minutes, doing several remarks. So the first remark is that, okay, so what we found here is that we saw that probability of the density of the eigenvalue gives you that the density of the eigenvalue concentrate around one specific form, and then that you have fluctuations with a cost which is exponential minus n square, and then, well, fluctuation cost which is exponential minus n to pull out one eigenvalue. So you can ask how much this is general. So if you take another ensemble of random matrices, what do we get? So this kind of results, the fact that the density concentrate is very, 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 very general. I mean, not that it concentrates around the semicircle, but that it concentrates somewhere is very general. The fact that the fluctuation are of order exponential minus n square, and the probability to pulling out one eigenvalue is exponential minus n, instead is general, but not so much in the sense that you must have some property of, let's say, the distribution of the elements. Typically, they should behave in a Gaussian way. They should go down fast enough. Otherwise, you can have different laws. Because you can have some elements of the matrix that become very, very big with high probability, and this will give you probability. It's easy to pull out eigenvalues. So this just to tell you, this is concentration of the density is very general. I mean, this large deviation is less general. Now, there is one, just to give you a concrete example, there is one other ensemble of random matrices that actually is even more useful, I think, for machine learning and data science than the one that I described. It's just that the one that I described was slightly more simple. This is why I chose it. And is the Wishart ensemble. And so I want to tell you just how all these things generalize to the Wishart case. So the Wishart case. So the Wishart matrix, which is Wij, that I'm going to define in this way, will be 1 over big T. So this big T has nothing to do with the temperature that I discussed before. Sum over mu, psi mu I, psi mu j, where the psi mu I are IID Gaussian variable, 0, 1. And so I go from 1 to n, and mu go from 1 to big T. And so these matrices are typically matrices that you find when you study, correlation matrix of data. And you also study them. You will see, I think it's when people, for example, will discuss, I think, in this school, maybe deep linear network, they will arise. Or even, deep or non-deep linear network, they will arise. And they can arise somehow if you consider the Hessian of problem in machine learning. So they arise much more than the one that I discussed, but they're actually very similar. So with a matrix like this, you can actually repeat all the things I have done exactly. So you can do the Dyson-Brownian motion for this problem. So the way to do it is simple. I mean, it's the same technique, the same idea that I gave you before. Construct a stochastic process such that W is, you get the distribution of the eigenvalue will be invariant. So it's easy since you have Gaussian here. What you should do is that you take psi mu I, and then you go from psi mu I, you add plus g mu I with a Gaussian variable. The sum is a Gaussian, so it's the same, and then you normalize. So by 1 over square root 1 plus dt. And g mu I is n0 dt. So if you do this, well, the new W that you construct after that, so this will be xi mu at time t, and this one would be xi mu I at time t plus dt, and from this you get the W at time t plus dt, and then you can repeat exactly what I did. You construct the Dyson-Brownian motion, but now for the Wishart matrix. And if you do it, if you want to see if you understood everything correctly in what I said, you should find at the end that P lambda 1 lambda n is going to be equal exponential of, so there is always the normalization in front, minus big T, so it's minus big T, sum over I from 1 to n, lambda I, plus T minus n minus 1 divided by 2, sum over I log of lambda I, plus sum over j less than k of log lambda j minus lambda k. Okay, so same term than before, these two instead are different. Okay, and this is true when t is n are both finite. Now the interesting thing is that if now you take the limit in which n go to infinity, t go to infinity, but the ratio is fixed, and the ratio q equal to n divided by t is fixed, then you find again the same property that I discussed before. So you find a large deviation principle with rate n square, with an f, which is different, but that you can compute just like we did before from this probability distribution. So you always have this interpretation in terms of n particle that moves, except that the potential is slightly different now. And then you can find also that lambda star, in this case you will have a lambda star of lambda, which is not exactly the semicircle, but it looks similar. It's lambda plus minus lambda. And then you have lambda minus lambda minus divided by 2 pi q lambda. And if I'm not mistaken, lambda plus and minus are 1 plus or minus square root of q square, where q is always big N divided by t. Okay. So this is, I think, is useful, and probably you will see this distribution, which is called the Marchenko-Pastur distribution. And I think Remy will tell you something a little bit this afternoon.
Yes, but in the case also where the covariance psi is not identical.
Okay, yes, because indeed, in this case, I mean, the covariance is the identity, which means this is just like pure noise. And indeed, when there is some structure in the data, then it becomes more interesting. So, well, this is the other thing I wanted to tell you. So I would like to conclude about the Dyson-Brownian motion. So why I chose to study this problem with the Dyson-Brownian motion. Yes, before you.
Before we move, can we solve this for like any kind of trapping? So I have these policy particles and I give you some trapping.
Yes. So at the beginning, I say that the GOE, one can write it general GOE like exponential minus trace of V of m. Yes, you can do it for generic V. So this will give not a Gaussian trapping, but a generic trapping. Yes.
And the Tucomi equation can also be solved exactly for like any kind of trappings?
The Tucomi equation, good question. So, no, I think it's not explicitly, I think, but I mean, you have an implicit equation. I mean, it's not, I mean, numerically it's easy. It's easy to do. Okay, so so there are many techniques in random matrix theory. So we saw the Dyson-Brownian motion, but there are others. So there is the resolvent technique, which is good when you take n going to infinity. I know there is one which is called supersymmetry for physicists, which is not completely rigorous, but I mean, somehow, part of it at least. So why Dyson-Brownian motion? So Dyson-Brownian motion, I wanted to show it to you. Well, first, because this way we start to do some dynamics together, since my lecture are about dynamics. But also, in recent years, there has been really a breakthrough in probability theory for people that study random matrices. And they study Dyson-Brownian motion, and really Dyson-Brownian motion for eigenvectors. This was the really important result. And there was a question before whether one can study the gaps between eigenvalues. So the gaps between eigenvalues are not, we are not interested in this problem for what we want to do. And I don't think in machine learning they are so important. But it's something that in random matrix theory in physics is very important because it's very universal. So you take very different random matrices that has very different rho star of lambda, but the statistics of the gaps between eigenvalues are the same. And the interesting thing is that they are the same then in physics problem, which you cannot solve, but they have exactly the same distribution. You can even find it in, I don't know, in number theory. I mean, you can relate some distribution between the prime numbers to the distribution between eigenvalues. So it's something that is very interesting in general, and which was difficult actually to prove mathematically. And so thanks to the Dyson-Brownian motion for eigenvectors, there are many proof of universal statistics that have been done. And in general, it's interesting really to see how the eigenvector moves. So this, I mean, the people that were really important in this work is Laszlo Erdős, Yao, all mathematicians, Burgader, and then others. And actually, if you want to give a look, if you are curious, you can see the Abel Symposium lecture of Erdős. I mean, it's kind of old, meaning that there have been many results. But I mean, if you Google Abel Symposium and Erdős, you will find some slides of Erdős that will tell you, I mean, all the things that have been able to do until 2012. But they have been really, they did a lot of things and very interesting things in recent years. All right, so I think I will stop here. And tomorrow we are going to start to see a little bit of dynamics in high-dimensional non-convex landscape. But before, I will have to finish a little bit on random matrix. So I will add a signal to the random matrix. And we are going to study a transition in which you can recover the signal from the statistical property of the random matrix or not, depending on the signal-to-noise ratio. OK, so thank you.